Okay, guys, so still in chapter 12, lesson 2. So we started out by talking about atoms, what are atoms, the structure of atoms, and how atoms pretty much are the smallest part of an element that still has the same properties of an element. And you did your lab where you kind of saw that different elements have different properties specific to that element, which helps us identify it. Today, we're going to be talking about how those different properties help us organize the elements into the periodic table. So first thing, each element has one of these squares. So I'm going to tell you how to decode these squares and see what information it actually gives you here. So the first thing they will have is the chemical name of the element. So this is the example of the hydrogen square. And yes, it says hydrogen. It will also have the chemical symbol, which is just a capital H for hydrogen. It will have the atomic number. The atomic number is extremely important because that is what identifies the element. No other element will have the same atomic number. And we're going to talk about what that atomic number here is here in a second. And then the average atomic mass. So sometimes it won't say average, but the atomic mass is an average of a couple different numbers that, again, we're going to talk about here in a second. But that atomic mass is essentially it has to do with the mass of the nucleus of that atom. So the first thing I want to address there on that square is that atomic number. So I said atomic numbers identify the element, but what is it? So the atomic number is the number of protons. The number of protons, remember that's the positive charged ones that are inside the nucleus. That's what identifies the element. You can change the electrons, you can change the neutrons, and it'll still be the same element. You can never change the number of protons. So we can use that number of protons in a stable atom to figure out how many neutrons and how many electrons it has. We're going to start with electrons. Since protons have a positive charge, right, of relatively +1, and electrons have a positive charge of relatively -1. If you have a neutral atom, meaning it's not charged, they'll be the same amount, right? So here we have lead, and lead has an atomic number of 82. That atomic number is the number of protons, meaning it will have 82 protons. Since it's a neutral atom, and we'll talk about atoms that are not neutral in a second, but since it is neutral, the positive charges will balance out the negative charges, so we'll have 82 electrons. Now, we have 8 protons in a neutral atom, which means we have 8 electrons, and our atomic number is 8. That element is oxygen. Same thing. We have 30 electrons in a neutral atom. We're going to have 30 protons to balance it out. Since we have 30 protons, that is our atomic number. And I believe that that is maybe zinc, atomic number 30. It is zinc. Look at that. I still remember the periodic table. Okay. There we go. So if you're asked, which is something you may see on a test, to give the number of protons or electrons and you have the atomic number, or to give the atomic number when you have protons or electrons, they're all going to be the same if it's a stable neutral atom. All right, cool. So now we have isotopes. This is what happens when you change that number of neutrons from what the periodic table has. And again, it'll still be the same element because unless you change the protons, it's the same element. And isotopes happen in nature naturally all the time. Think like carbon. We have so many different types of carbons from 13. 12 is the most common when we think of carbon 14 because you name isotopes based on the new mass. So the mass number or atomic mass, you can see them interchangeably. They refer to the same thing. So atomic mass, excuse my handwriting, same thing. It's the sum of your protons and neutrons because that is where all your mass is in the atom. The electrons are so small that it's negligible. So we just say it's relatively zero. So when we're talking about the mass, we just include the protons and the neutrons. Remember that. So just how we used atomic number to figure out protons and electrons, you're going to use atomic mass or mass number to figure out protons and neutrons. And whatever that number is together, you could just subtract to find the other one. So for a potassium-39 isotope, this is your mass number, right? And so if they gave you 19 protons, you could subtract 19 from 39 and realize, oh, that means I must have 20 neutrons. When you're trying to figure out protons and neutrons, electrons, really, you don't need to consider those unless you're trying to figure out the number of neutrons. But this is just an example of 3 different potassium isotopes, because remember, isotopes are atoms with a different number of neutrons. So notice everything else, the protons and the electrons are 19 all the way across. It's those neutrons that have changed. And potassium is one of those fun elements where the symbol doesn't necessarily match the name. So the symbol is K, which I always love those ones. Okay, so this is a good exercise of something you might be asked to do as well on a homework assignment or a test. I'm not going to go through all of them, but I'll do a couple of these so you can see how it's done. So this wants us to determine the number of protons, electrons, and neutrons, right? Determine the number of protons, electrons, and neutrons. And name the isotope and give its symbol. So there's a couple different things here. So let's start with our neon. And we have an atomic number of 10, right? Remember, atomic number is your protons. So for protons, we'll have 10. And since it's stable, we're going to have the same number of electrons. Now for our neutrons, remember mass number, that's this guy, is our protons plus our neutrons. So if we have 10 protons, that means we're going to have 12 neutrons. There we go. We did the first part. Now we need to name the isotope. Remember the isotope, you just name it. So neon, and then you use the mass number. Neon 22 is the name of this isotope. And the last part is the symbol. When you're doing the symbol of an isotope, you're going to write the chemical symbol that you would get off the square. And you will be able to use a periodic table. I don't require my middle schoolers to memorize the periodic table like my high schoolers, so you will be allowed to use one on your homework, test, quiz, whatever. And then at the bottom left corner, you're going to put the atomic number. Then at the top, you're going to put the mass number. All right, so that's how you would do neon. Let's do calcium. Protons, remember, is your atomic number, so that's 20. Electrons, since it's stable, it's going to match. Neutrons, your mass number is 46. So 46 minus your 20 protons is going to give you 26 neutrons. The name is calcium 46. And your symbol would be Ca. Calcium's 20 and 46. There you go. And that's how you would do all of those. So the periodic table is organized into vertical columns and horizontal rows. So the vertical columns are called groups. Now, these groups all share similar properties. So like the first vertical row, each one has a different name too. Sometimes they call them families, but we're going to call them groups. Like the first group is called your alkaline earth metals. And all of those behave similarly when they're reacting. And we'll talk about why here in a second. But that trend repeats periodically because every row that you get to is going to have the same properties. That's where we get the term periodic table. The periodic table is organized in order by increasing atomic number. So if you read from left to right, down the rows, you will notice that the atomic numbers increase. Originally, they were organized by atomic mass until they realized that there were a couple different elements that didn't fit that pattern, and so they changed it to atomic numbers. So 18 groups, each different group behaves similarly and has similar properties. We're not going to talk about the name of each of the groups in this lesson, but it is something to be prepared for and to know exists. So In a neutral atom, we talked about how the number of electrons equals the number of protons because protons positive, electrons negative, so they balance out, so they have something neutral. Um, and we talked about in the last lesson the whole electron cloud and how we don't know exactly where the electrons are, but we can tell what energy levels they are. And remember, we said that they don't orbit in these specific planetary orbits. It's like these different shapes as well. But this is an energy diagram that literally just to show you the energy levels they are in. Do not think that they are lined up perfectly like this in perfect circles. This is just a way of organizing their energy levels. And as energy levels go up, you can hold more electrons there. Okay, so at the outer energy level, that is where we're going to have something called our outer electrons or valence electrons. Every atom in the same group, so that first vertical column, we'll use as example group 1, will all have the same number of electrons in their outermost level. In that outermost shell, they'll have the same number. So group 1 will have one of them. And we'll come back to that idea here in a second. But everybody really wants to have 8. 8 is the magic number that you want to have on your outermost shell. Again, we'll talk more about that when we get to chemical reactions and why that's important and how that comes into play with chemical reactions. But everybody wants to have 8, but you figure out how many they have based on which group that they are in. So this is a little bit of what I was just saying on the last slide. Elements in the same group have the same number of electrons on the outer shell, valence electrons we call them, and that determines their chemical properties, so basically how they react. So you can have more energy levels than this. This is just showing you the amount of electrons that can be held in each energy level, each of the first 4 energy levels. You don't need to memorize this. This is just showing you as you go up in energy levels, you can hold more electrons. That has to do with the type of orbital, something you'll learn in chemistry, but different types of orbitals can hold different amounts of electrons, and different elements based on where they are on the periodic table have a different number of different types of orbitals. So this is a small part of the periodic table. We've cut out the middle part where all the metals are because they have a slightly different pattern. So we're going to ignore the metals for right now, and we'll come back to them in another lesson. So again, like I said, these guys over here, every single vertical row, so we'll just use group 1, as an example. So these guys right here all have similar chemical properties, and they all have 1 electron on their outermost shell. These guys over here, we call those the noble gases. Everybody wants to be noble. They have 8. One way that you can figure out how many valence electrons or outer electrons that an element has is skip over the metals, the guys in the middle that we don't have, and you can just count across, right? So these guys have 1, 2, 3, 4, 5, 6, 7, and these guys have 8 on the outer shell. That is going to be very important when we get to reactivity and how things combine together. So again, this is just repeating what I said, showing you that, okay, so these guys over here are all going to have 2 valence, these guys over here are all going to have 3 valence, and it continues. So now, something we call an electron diagram. This is basically a way of drawing a chemical symbol so that you know how many valence electrons something has. So for these guys, these are all our group 1 elements. Since they're all in group 1, they all have 1 valence electron, so we put a dot to represent the valence electron. Dots you're going to want to put in pairs of 2. So no side of an element should have more than 2. So for example, if I were to have the noble gas neon and I wanted to put all 8, the electron diagram would look like that. So here's another one, an example of a halogen, which is group 17, right before the noble gases of chlorine. And it's just missing 1, so it has 7 valence electrons there. Now, again, we're not at reactivity yet, but they just threw in an example here so you can kind of see how that works. So this is our atom for chlorine. Sodium is a group 1, which means it has 1 valence electron. If these things were to react and create sodium chloride, which is table salt, this electron could fit real nice right there. And that's how we get the ion charges. Because remember, ions are atoms that have gained or lost an electron. So now they're both ions. That's how chemical bonding works. It's one type of chemical bonding. So now on the different parts of the periodic table, this is a whole periodic table that you probably are most familiar with seeing. What we've just been looking at are these sections right here and these sections right here. We skipped the metals, all right? So when you're counting for valence electrons, you'd count 1, 2, 3, 4, all the way to 8. These guys in the middle have a different way of figuring that out. But again, these are your groups going up and down. Those have similar chemical properties. These going across are called periods, all right? And those are numbered 2. 1, 2, 3, 4, 5, 6, 7 periods. You'll see those on a periodic table numbered. This section here, your lanthanides and actinides, it's just really long. Sometimes you might not even find a periodic table that's this extended, but they kind of fit in here where these two gaps are. So they fit across there. They're still metals. So the periodic table, because the properties repeat periodically, we end up with these groups that have similar properties aside from just the ones in their vertical group. So over here on the right, we have our nonmetals. So a lot of gases over here. We have our metalloids in the green, which is kind of things that are like a hybrid metal, non-metal. Then in the blue section here, we have all our metals, and we have a bunch of different types of metals. The ones right in the middle, like here to here, we call our transition metals. These guys on the left are alkaline and our alkali earth metals. And yeah, those are different groups of the periodic table. So, and the last time I'll say this because this is very important, everything in the same group, so those vertical columns, will have similar properties because of the number of outer electrons they have. That determines how reactive they are. Some elements, though, that group 18, those noble gases that have that full 8 outer electrons, are unreactive. And that's because, remember, I just showed you how that sodium would react with that chlorine? Well, these guys already have 8. Who do they want to react with? No one. So that is how you get an unreactive element. So that is lesson 2. Take your notes, watch the video I posted, and you're done.